story where I'd forgotten what day it was. I looked out the window and I saw 4 buses. And then I figured out what the posterior probability was of it being a weekday or being a weekend. Hopefully it made that story more complicated by saying, actually, I'm not sure how many buses a week is or a weekday, but I thought that might be. And then we made it more interesting by saying, I think there's 4 buses and I think there's 3. And then we started to look at some other problems that we could investigate. Trying to say what my motivations were. I talked about these 3 motivations. One is about understanding what statistical models mean, in particular what parts of them mean when we put them together. We've got a complicated statistical model, hundreds of lines long. What do the individual bits of it mean? Can we suggest new complex statistical models that statisticians? And can we quickly and easily prototype things so that we can experiment with models? So you saw last time we looked at, for example, 2D physics simulation, and I could very easily quickly write down a probabilistic program specifying that I wanted the ball to land on the cup, and I could quickly experiment and prototype with it. A simple inference algorithm. One of the kind of buzzwords of why engineering with probabilistic programming could be a good idea is that the model is separate from the inference. So we can look at the model and check it's correct. The model is the probabilistic program. Separately from looking at the inference algorithm and understanding what that's doing. So we can reason about what kind of model we want to have, what kind of things we want to say, separately from doing the inference. And that's a step forward in some ways from traditional way of doing it. Yeah.
So that would be, the model would be like the statistical corrections of the model?
Well, so to understand correctness, one thing is to understand whether the model is suitable. There's all kinds of notions of correctness in models, which I don't know if I want to go into now. We can understand whether the model is suitable in the abstract. Then there's a separate question of whether the inference algorithm is going to properly explore the model, and that's what we're going to talk about in more detail. Yeah?
Terminological question. Why is it called inference? I mean, if it's a program, it has a denotation.
Yeah.
Why not calling it interpretation or evaluation or why is it termed inference?
Yeah, so it's called inference. I think those words would be good. I mean, the people who started this stuff people. Maybe that's why. But also it's called inference because it's all about Bayes' law. Someone remember Bayes' law? Okay. Can someone tell me what it is?
P of A given B equals to P of B given A.
Yeah.
Divided by P of B times P of A.
Okay. In words? Oh, let's give them a run. That's very arty. In words? Somebody want to say it in words? Yeah.
Posterior probability is proportional to the likelihood of the variance.
Great, yeah. So the posterior is proportional to the likelihood times the prior. So when I run a simulation, I'm thinking of my probabilistic programming. My probabilistic program has a statistical model describing this, okay? And I want to figure out what's my posterior probability distribution, and that's called inference. Okay. So probabilistic programming, just to remember if you sort of need a bit of a reminder, you've done some other things since we last met, I think. It's all about adding to a programming language, so it's a normal programming language, plus things corresponding to the clauses of Bayes' law, which means sampling from probability distributions, we described our prior, including observations, and then finding a normalizing constant so that we can deal with this proportionality. And that finding a normalizing constant is the expensive thing, and that's what we're going to talk about. I realised that last lecture I showed you some programs and stuff and told you to download the Haskell interpreter. We didn't really talk about where these ideas come from. Perhaps I should spend a few minutes doing that. I think Andy probably talked about this to some extent as well. So probabilistic programming probably started in the 90s with the bugs language. But for me, But where it really began to become very general was around 10 years ago, 12 years ago, at MIT, the church language which was instigated by Josh Tenenbaum, who's a psychologist, and he wants to build models of cognition, and he wanted a language for doing that. And so he built this very general purpose language, Church, which is based on Lisp. Okay. Lots of other languages, I mean, some languages came before Church, lots of languages came afterwards. In Oxford, my collaborator Frank Wood came up with a language called Anglican. So there's a joke there. The church language, I believe, was named after Alonzo Church. We all know. Probably wouldn't know. But it's also a building where people worship. An Anglican, a base was an Anglican vicar. So Frank thought it would be a good name for the language. Right. So Anglican's based over closure, and I was using that actually for a long time to experiment with stuff, but I got really frustrated by the lack of types in closure. And I find the types really help to explain what kind of model we've got. And so then I started using Haskell. I started with Studia has a library called Monad Bayes, which is quite a powerful library that performs very well and lets you combine all sorts of inference algorithms. But for the purposes of this course, I've cut it down to just 20 lines. So if you want, you can go and look at Adam Scibia's Monad Bayes Haskell library, or you can just use the simple thing that I've got. So Frank has been working on Anglican for 5-10 years. No, not 7 years. And so some of the examples I took in the last lecture, program induction, for example, and the 2D physics model, I was inspired by examples that Frank has been using to demonstrate Anglican. I just want to be clear about that. In fact, Frank has now not gone beyond 2D physics. He's now got a model of the Large Hadron Collider. So these things really are going somewhere. Those examples came up in a machine learning summer school that Frank ran. You might like to look at the notes or the slides or the course material of that if that's kind of interesting to you. He's also got a book that you can look at in the archive. So anyway, let's carry on with probabilistic programming. What I want to do today is look at experimenting with inference. And let me start by recapping an example that we saw last time, which is Bayesian linear regression. Okay, let me remind you what it was. Last time I looked at it in Haskell, but now let me write it on the board. And in Haskell, I was using some map and fold, or maybe just map. It makes it look a little bit more complicated, but it's a bit short. So anyway, I'll try it out without any map or any fancy stuff. So, I want to know which function fit those points. And this is a Bayesian regression problem. So I'm not interested specifically in which function best fits those points, but rather what distribution of functions, what posterior probability we could have on the space of functions that might have generated those points. Okay? Oh, you mean this one here? Yeah. That's all. So let me write a program for Bayesian linear regression. So I sample the linear function has two parameters, its slope and its intercept. Let's say, I don't know what the slope should be, but it's about 0, plus or minus 9. I don't know what the intercept should be, but let's also sample it from a normal distribution. And then I define a function, a linear function, ax plus b. And now I'm going to start. So this, so far, just picks out some random linear functions that go all over the place. You might wonder, why did I pick normal? Well, I wanted to say, I'm not really sure what these things are. Maybe I would have liked to have been able to say, I don't know what A is, it could be any real number. But that doesn't form a probability distribution. There's no uniform distribution across all the real numbers. So we need to be a little bit more precise. And I do have a belief, when I look at the points, that the slope is probably around 0 plus or minus 10. And I have some belief that the intercept is around this kind of region, 0 plus or minus 10. But the normal distribution has an infinite support. So I'm not ruling anything out, I'm just giving some belief. I could argue maybe with the central limit theorem that where A and B come from comes from some noisy stuff, and I don't know exactly what they are. But another point is, and we'll see this in a second, when you've got enough data, the prior starts to become less and less important. So the fact I put these things here, as we'll see in a second, starts to become less and less important when we do our algorithms. Now that's just the prior, and let's include the observations. So I want to observe things like f0 equals, you get the data points up, 0.6 is that first data point. And I want to keep going and observe all of the values of f that I've got, right the way up to f6 is right over 8.4. There's something wrong with what I've written here. Anyone spot what's wrong? Yep.
Checking quality of real numbers.
Yeah, it's a bit naughty, but yeah. Anything else wrong? Yep.
If it doesn't follow straight on directly on the line,
Yeah.
it's not going to work, right?
Yeah, so these observations are all going to fail. So these observations together are going to fail because these points don't fit on the lines. There's no line that satisfies all of these observations. And so to come back to your point about checking the quality of real numbers, there is kind of a real thing. In that, well, what does this really mean? We talked about rejection sampling. Does it mean you're going to reject just those traces where f0 is 0.6? None of them will actually, that's very, very unlikely that you encounter that. So what we do in Bayesian linear regression is to say we observe 0.6 coming from, let's say again, a normal distribution, although you could fiddle with that a little bit. Let's say with mean f0, but with standard deviation, let's say 1. I've got a picture, so I've got a picture of a normal distribution here. Yeah, okay. So here's that flat prior, okay, which is the red line, and the blue line is how we're going to do our conditioning. I'm going to say f0 is about where we thought it was, but there's a bit of wiggle room. Not that much wiggle room, but there's a bit of wiggle room. Okay, so we go through and replace all of those. Oh, is that 8.2? Is that right? Normal f6 and standard deviation. So I call f6, that's my mean of my normal distribution, and I observe the value of it. So the question you might ask is, why were these data points, why were they not collinear? Maybe it's because the guy who was measuring whatever it was they were measuring was rubbish at measuring, right? Or maybe it's because there's something in the actual real world that's caused them not to be linear. So if it was that the guy who was measuring them was rubbish, then we've chosen 1 as the standard deviation of what his measurement behavior is. We could have sampled that from something else. So if we sample that from an inverse gamma distribution, I think this is what's called a student T observation. So we can start to build more complex models where we do things like that. But yeah.
Why do you have, like, I would expect you to, like, observe f0 from normal 0.6.
Yeah, okay. Is it it's exactly the same. We'll talk about semantics this afternoon. Which way? Normal. We can debate about which one it should be, but for the normal distribution, actually, write out the formula for the normal distribution, you'll see that. I don't think we'll do that now, okay. So that's linear regression. Yeah, any questions about Bayesian linear regression? So just to emphasize, this picture I've drawn on the slide here is 500 draws from the posterior distribution. So you can see, you can get a sense, get a sense of where the mean is, you can get a sense of what the variance is, but actually it's a more complicated distribution than just that. Yep.
They're still using the weighted multi-color.
So how did I generate this? I generated it using the algorithm I'm going to show you in a minute. You could generate using the weighted multi-color, it would take a long time. We'll see why that is in a second. Yep.
Just to clarify, sorry, so the priors are drawn from normal distributions with the variances 3.
Yeah.
Why is the variance 1 for the observations?
Yeah. Yeah. So the prior says that I don't really know what A and B are. So this orange curve where I'm really not really sure what they are. with the observations, I'm quite sure that the observations are correct. So that's why I've put a smaller standard deviation for the observations.
Okay.
I mean, actually 1 is still quite big. It should probably, you can see there's a lot of error allowed. Yeah. You should probably make it a little bit smaller. Yeah.
What does the word from mean in this context?
Right. So what happens is when I actually write this in Haskell, I'll write score of normal PDF. That's the density function of the normal distribution, 1 over square root 2 pi theta e to the minus. And that takes 3 arguments, f0, the observation value, and then 0.6, which is the mean, and 1, which is the standard deviation. So when I write this observe command, right, I'm thinking of it in this way. It means weight the trace by the value of the density function at the observation. Weight the trace by the value of the density function at the observation. Some languages let you write observe, and then it will compile that down to this score. Any more questions? Okay, so let's carry on talking about simulation. So I want to show you how we get from that program to this plot, this posterior distribution. Okay, so last time we talked about weighted Monte Carlo, where we run the program and then we weight the traces according to the score. So let's just remind ourselves what weighted Monte Carlo is. Weighted Monte Carlo. So what would we do? We run the program lots of times, k times. Each time we run it, whenever we see a sample, in this case it's going to be 2 samples from a normal distribution, so we're going to sample twice, A and B, from normal distributions. We'll talk a little bit later how we do that, but let's just leave it at that for now. And then we carry on down the program. We let fx be ax plus b. A and b have been chosen now on this particular run. And then we weight the trace by the score. So then we weight the trace, the run, right, by the observations. Now, last time there was only 1 observation, I think, in the example we went through by hand. Here there's 7 observations. So we're going to weight the run by the density of the normal distribution at each of those 7 observation points. By the PDF, for the likelihood at each observation point. Okay. Now what does it mean to weight things multiple times? It means to multiply the weights. So that means what we end up with is something like this. 1 over 2 pi, sigma is 1, so that's okay. This is, if you don't remember, the density of the normal distribution, f0 minus, what is it, 0.6 squared times, blah, 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 times 1 over root 2 pi p to the minus of f6 minus 8.2 squared. I hope I got that. Okay. Now here there's only 7 samples, there's only 7 things to multiply. What if we've got 1,000 data points? Anyone see a problem that might start happening?
Those small weights.
Yes, that's what you were about to say. Yeah, yeah. Yeah, well, right, so if I have a weight of somewhere around the region of 0.1, I multiply that 1,000 times, I end up with like 10 to the minus 1,000 or something like that. That's way too small for a double precision number. But it's easy to deal with, you just take log numbers. So Haskell even has a library that's ready to use to do log numbers. You just deal with the log to the weight instead of the actual weight, and then you add them instead of multiplying. Everything just works. So I don't need to talk about that. It's just a trick to get things to work. Okay. So that's weighted Monte Carlo. Now, how do we actually draw from the posterior? So we built up, by running weighted Monte Carlo, these samples, x1, f, isn't it? f1 with a weight, all the way up to fk with a weight. There might be a million of those or whatever. And now I want to draw from a posterior. So what do? Well, I build a probability distribution out of these samples that I've found. So the probability distribution is, let me write the normalized afterwards, the sum of the Dirac distribution, that's the distribution that I'm certain it's Fi. That's definitely the thing it is. Okay? Then I multiply that by the weight, and I'm going to add together all of those across all of the samples I've drawn from the trace. That doesn't sum to, that doesn't have an overall weight of 1, so then I divide it by a normalized. Okay? So that's sometimes called an empirical distribution. And as k goes to infinity, this, which is a random measure, because each time I run the simulation, k times I'll get different things, goes towards the true posterior. Let's have a look then at what weighted simulation looks like. So here I drew, I think, 10,000 points from my weighted simulation. And what I've done is to plot them, rather than plotting them as lines, I've plotted the slope and the intercept on two separate axes. So remember, each f, it looks like this. A1x plus b1. Right? A2x plus b2f, akx plus b. Each of these f's is a function with two parameters. So because it's got two parameters, we can easily visualize it on the plane. So this is the slope, and this is the intercept. Each one of these points corresponds to one of the samples from my weighted Monte Carlo simulation. And I've coloured the points by their weight. So only these bits in this region here, with a slope around this area and an intercept around this area, are actually any good. All of these are really, really rubbish. And in fact, they weren't visible. I had to bump up their colour to make them visible. So there's really very wasteful to explore this area. We're talking like 10 to the minus 100 or something like that in terms of how rubbish. The other thing I want to just point out from here is this is probably the true posterior, but you can see the prior lurking here as well. This shape here is the shape of a multivariate Gaussian with a normal with a mean of 0, 0 and a variance of 3, a standard deviation of 3, 3. So that's the prior you can see still lurking there, but it's got very, very faint. As I said, I had to bump it up so that you could see it. It's still lurking there. As we add more and more data, it will become even more faint and even less important. But the real weight is lying in this region here. Let's just zoom in. Okay, now I had to go to, I think, 100,000 samples to see a picture like this. Or that's zoomed in. Okay, and then you can start to see the shape of the posterior. So, with 100,000 samples, you know, this is an extremely wasteful way of drawing from a posterior, because a lot of them are going to get, this is going to be a very big thing to do. So we need to do better. Any questions just now about weighted simulation? So what I'm going to do now is to try to segue towards a better simulation algorithm, Metropolis-Hastings, and to do that by first looking at some more naive simulation algorithms that already don't work so well but are a little bit better than this. So the first one I want to look at is a generalization of rejection sampling, and a version of rejection sampling that does work in this continuous set. Sometimes it's called accept reject Monte Carlo, sometimes it's called rejection sampling, sometimes it's called plain Monte Carlo. So what's that algorithm? Okay, so sorry, before I say that, let me just emphasize one important problem with weighted sampling. And that's that before we can start drawing anything from the posterior, we have to find this normalizing piece. Right? We can't start drawing anything, we can't spit out any draws from the posterior until we've got all of our K samples, because we can't start doing anything until we know what the normalizing constant is. So that's really bad. We need that. So let me show you one that works a little bit. This is what should we call rejection, weighted rejection.
Sorry, question.
Yeah.
Why can't you do that? Do this online, right?
Why
As
can't
the,
we?
you can maintain the.
Yeah, well, maybe that's sort of what weighted rejection does. Yeah, you're right. If I did it naively, like I've read it, don't know that you might see a massive weight later on, so you have to be quite careful. Okay, so weighted regression, what do we do? So we do a similar thing. Each time we run the program, we sample A and B from the normal prior. Now we suppose we know an upper bound on what the likelihood could be, or what the weight could possibly be. Okay, let's look at the here. Well, in this case, we've only got sort of a few things that we're going to use. And in that case, it might be better to do it in this way. And so we know what the upper bound could possibly be on what the likelihood will be. So we've got, suppose we've got, let's call it a W max, which is the max weight that we'll ever see. Could even be bigger than the max weight that we'll ever see. Is known. It's not always the case. Sometimes there's no max weight, and then you don't know what it's going to be. Right. Now, I figure out my score. So, find the weight of this run. That's what I was calling WI. And I do that by calculating the likelihood, the density function at the observation points. And now, we toss a biased coin, where the bias is the difference, is the ratio, of the weight of this trace with the max weight. And if that coin comes back heads, we spit out this sample, which is a function lambda x a I x plus b I. Otherwise, well, let me number these lines. 1, 2, 3, 4, 5, 6. Go to 1. Okay. So we do a similar thing to weighted sampling, but we can spit this out straight away with the probability W1 over W max. And if we don't succeed in that very early trial, we just won't spit that one out. We'll just reject it. So we just randomly reject some of the samples, and the probability of rejecting them is proportional to the weights. So that's a method that works. It's also not very good, but it's at least we can easily do it without figuring out a maximum weight. We do need to, without figuring out this sum of the weights, but we do need to know the weight, the maximum. Yep.
Do you just spit out one then?
Spin out it. This
You
function.
just add one function,
And then go to line 1. This is a programming language that I thought maybe I shouldn't say go to.
maybe?
Yeah.
Like if you spit it out, otherwise.
I don't spit anything out. So maybe for a while I don't spit anything out, I just keep looping. But at some point, chances are I'll spit. Yeah.
What do you get as a benefit from doing this? Because
It's a benefit because it helps me segue to the next.
Sorry, what?
It helps me move to what I want to say next.
Okay.
Yep.
How do you guarantee generation?
Sorry?
How do you guarantee
So I guess it's not guaranteed totally, but almost surely this will terminate. Because the probability of going on forever gets smaller and smaller and smaller. So it's almost sure termination. Good point. Any more questions? Yep.
why is this different? You can't measure things like runtime. So you can't sample.
Yeah, no.
This is a bit less useful in the time running time.
Yeah. I'm not defending this, and I don't think I even implemented it. Okay, but I just want to show it you as a way to stepping, because we can now step quite quickly from this one to a much better output. Any questions? So notice this thing is going to spit out some samples from the posterior. I could have used it. I accept something. Actually, I accept it twice. That doesn't change the asymptotic distribution. It just doubled everything. Each time we're going to spit out something, we spit it out twice. And of course, it's even more rubbish, but it doesn't change the asymptotic distribution. This is okay. One last observation I want to make. I could change line 5 to spit out the result, lambda x, AIX plus B, I, some random number of times. And if that number of times, each time I'm about to spit out lambda x, AIX plus BI, I draw something from some distribution on the natural numbers, maybe a Poisson distribution or something, and then I spit it out that number of times. And as long as that random number of times is independent of A and B, that's okay. If you think about it just a little bit, you'll see the asymptotic distribution is going to be the same. It's going to be a bit rubbish, but it's the asymptotic distribution is going to be the same. This is okay. And with that observation, we can immediately write down the Metropolis-Hastings. Oh, school now. So, the Metropolis-Hastings algorithm, this is the most simple kind of Metropolis-Hastings algorithm. We're going to look, we'll have a little break in a minute, then we'll look at some more advanced kinds of Metropolis-Hastings. But multi-site Metropolis-Hastings. 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 Works as follows. So we've got some answer that we've seen before, and we want to know whether to keep spitting it out again. So we generate, by running a rejection, so by running a weighted sampling, we generate some Fi and Wi. And then we want to know what to spit out. So with Metropolis-Hastings, every step you spit something out. If, well, to start with, I'll use this. If this balloon trial succeeds, it's the same one as before. Then I spit out my new sample. Otherwise, spit out the previous value. Okay? So we do this draw exactly the same, and then if it succeeds as before, we spit out Fi, that's if it fails, we toss the coin, it came back tails, then we spit out the previous value. Why is that okay? Well, it's okay because we're going to end up repeating the previous value some random number of times. That random number is independent of AI and BI. And so, this is exactly what we've done. We've changed line 5 in this program to repeat each thing some random number of times where that random number is independent of AI and BI. So this is the multi-site Metropolis-Hastings algorithm. Anyway, so I can improve it slightly. Maybe some of you have seen Metropolis-Hastings before. I've seen this slight improvement of it. Let me write down the lines. 1, 2, 3. And the slight improvement is to say change, improvement, change line 2. Say, rather than merely of the weight of this sample over the max weights, you could say if the weight of this sample is bigger than the weight of the previous sample, then we're definitely going to spit out a new thing. We found something better, let's spit it out. If the weight of the new sample is worse than the previous sample, what we could say is don't spit it out, but we're not going to say that. We're going to be a bit random about it, and we might spit it out. Or, and now we come to the Metropolis ratio. Well, we toss a coin not with wi over w max, but wi over wi minus 1. Then, alright, so that's line 2. Okay, so if, rather than saying if this coin toss came up true, we spit out the new thing, we say if the new thing is better, we spit it out, or if this Metropolis test comes back with a true. So this is a single site, multi-site Metropolis-Hastings. What do I want to say now? Okay, let's, so just before I'll have a little break now. But one important point about this improvement, we no longer need to know the max weight. This just depends on the previous weight. Okay, so let's have a fight. Oh, any questions? Yeah.
Could you give an intuition for why in the asymptotics,
Yeah.
the distribution doesn't change if you sample independently from AI and BI? And if that's true,
Yeah.
then why is it valid? Because my previous FI, the not independent system, the current FI, seems to both drop in the same prior.
No, it's an independent draw. And we'll see it in a minute. We'll say what we're going to simplify.
Can you just automatically spit out the first one?
Sorry?
Do you automatically spit out the first one?
Oh, you're worried about how we start this?
Yeah.
What's F0? Yeah, it doesn't really matter. Yeah, so one thing to say about Metropolis-Hastings is maybe it spits out F0 quite a few times to start with, but you just chose arbitrarily or randomly. So what you usually do in Metropolis-Hastings is you burn it in. You run it for maybe 10,000 steps until hopefully it's picked up something like this. We'll see that in a second. We'll have to wait. Is there another question? Yeah.
If your priors are really bad, you're just going to keep sampling really
Yeah.
low. Right? Okay, yeah.
So we'll talk about how to make this better in a second.
Oh, yeah, okay.
Or Yep.
So this max
Yeah, that's the problem. That's the problem with this method, with this. But when we do this improvement to Metropolis-Hastings, we no longer need the maximum. We just divide by the wi over wi minus 1. So no longer do we need max weight. Yeah.
What about this is multi-site?
Sorry?
What about this is multi-site?
We'll see. Okay, so let's have a break until 55, I guess. And then we'll come back and we'll look at a single site, which is not, it's not much more that we need to do. Let's continue. We want to talk now about the single site Metropolis-Hastings algorithm for probabilistic programs. Yeah. Yeah.
You said provided that the Bernoulli flip is independent of A and B.
Bernoulli flip? No. The number of times I spit the same thing out. Yep. And down here, the number of times I spit out fi minus 1 is independent of w.
So why is the Bernoulli flip like a valid thing to do?
Why is it valid? What do you mean?
Well, why does this produce the same good result?
You mean this algorithm? Why is it correct? Yeah, I think I want to move on, but we can talk about that later. Yep.
There's probably some result about the asymptotics, the speed of convergence. Will you say something about this?
We'll talk about, I think that this is the Achilles heel. Because for general purpose probabilistic programming, we'll see a bit about that, but statisticians typically look at specific models and provide asymptotic results or specific classes in model. Now I'm letting you write arbitrary models, and the asymptotics is difficult. Yeah. So we know it will converge, but we've got no idea when. Yeah. In fact, if we knew when, we could solve the halting problem.
I just want to clarify how you start the process.
Yeah.
WI over
Yeah. Yeah.
So is it that the first time you
it doesn't really matter what you pick to start with, because what we're interested in is the asymptotic distribution, the distribution that we get after we run it for a long time. So you're going to maybe pick something stupid to start with. It's going to come up a few times, but eventually it will, in the scale of things, it will wash out. Maybe you pick it randomly. Maybe you have a good starting point. Yeah. Okay. So I need to. Let me see. Yeah. Okay. I want to make some simplifying assumptions just to get things moving. Then we get rid of them if there's time. So first of all, I'm going to assume. Actually, there's only one simplifying assumption. So simplifying assumption. That's quite a major one, but yeah. Assume the number of sample statements in your program is fixed exactly at, let's say, n. Okay? So this now turns this into a parametric statistical problem. We have a fixed number of parameters. Which I realized yesterday in Nick's lecture that people in programming languages talk about parametric polymorphism, right? And it's nothing to do with parametric polymorphism. In fact, it's kind of opposite. So parametric statistics is easier than non-parametric statistics. Parametric polymorphism is harder than non-parametric polymorphism. Yeah, so that's an assumption I'm going to make just to start with, just to get things moving. Assume the number of sample statements is fixed. In this example, there's 2 sample statements. So this example we can deal with in the piecewise linear functions. The number of sample statements might vary depending on how many change points there are, and so then the number of sample statements is not fixed. That becomes non-parametric. But let's keep it fixed for now. In your program. Okay, now, in each run of the program, there's only going to be, let's say, 2 or 10 or whatever sample statements. And I want to make an observation to simplify things. Observation. This is not an observation in the statistical sense, it's an observation in the rhetorical sense. Let's observe something that it's always good enough. If you know how to sample from a uniform distribution on the unit interval, you know how to sample from any distribution. So it's enough to sample from uniform distributions on the unit interval. Okay, let me show you. I've got a little picture why that's okay. So if I have a sample from a uniform distribution on the unit interval, what does that look like? Okay. There's the unit interval. Whoa. Goes from 0 to 1. And every number between 0 and 1 is equiprobable. Okay. So once we've got that, we can build any other distribution. For example, if I sample from the uniform distribution a number between 0 and 1, and then I apply this step function that I've shown on the right-hand side of the screen, then I'll get a Bernoulli sample, right, with probability 2/7 I'll get true, and with probability 5/7 I'll get 0. If I sample from a uniform distribution between 0 and 1, and then I apply to that thing that I just sampled this function here, which is the inverse commutative distribution density function of the Gaussian, I'll get a sample from the normal distribution with mean 0 and standard deviation 3. You see, when I pick things uniformly down here, I'll end up concentrating around 0 at the top here, but still spread between 0 and 10 and probably going a bit further. Some chance. Okay. So that's a method that's very useful to just simplify things. And in fact, I didn't show it you, but in the implementation I have in Haskell, that's exactly what I do. My main sample thing is just a sample from a uniform distribution, and then I do the other things that just derive, the syntax that just deals with that. We let the programming language deal with all the other stuff. Okay. So that's a simplifying assumption and an observation. And now let's think about what's going on. So when we run through our Metropolis-Hastings algorithm, we've got these samples that we've drawn on each run, the A and the B. Okay. So the Metropolis-Hastings algorithm gives us a search across R2, the real plane. So now, another observation I want to make is that when we look at our program, we can understand what it means in terms of something deterministic. So now supposing all the things are drawn from 0, 1, given a collection of seeds, there's only n sample statements, so it says, given seeds in here, which we're then going to use the cumulative distributions functions or whatever, we can deterministically find fi and wi. Okay, if you tell me in advance what all the sample statements are going to give me, then I can deterministically tell you what's going to be the output, the resulting function, and what's going to be the weight. It's a deterministic relationship. Okay, in other words, we have functions like this that, given the sample space, give us the result, which is, I don't know what type it's got, maybe it's a function type or whatever, and give me a weight. So weight and result. Okay. So now I'm going to run the Metropolis-Hastings algorithm over the seed space. Okay, so on each time I run, I'm going to, instead of going through, I initially said I'm going to go through, where are we? Oh yeah, each time I'm going to sample AI and BI. What I'll do instead is I'll just resample from a uniform distribution across the unit cube. Okay. Now I brought along some cards to demonstrate what's going on. Okay, let me pick 5. So multi-site Metropolis-Hastings works like this. I'm playing a game, I don't know, poker or whatever, and I've got this hand, okay, and that's not bad, and I want to decide should I change it or not, okay. So I draw another hand, 5 cards, and that's going to have a weight, maybe a different weight. Okay, another 5 cards, and I've got to decide should I switch or should I stick, okay. And if this hand is better, Metropolis-Hastings multi-site says I'm going to choose the better hand. If this hand is worse, Metropolis-Hastings is a random optimization algorithm. It's going to say, with some chance, still take it, still take the other hand. So it says, if the hand you're offered is better, take it. If the hand you're offered is worse, take it with some small chance, or maybe a big chance. Can anyone think of a way to do a better than what I just described using the cards?
Oh.
Yep.
So you get to, I guess like what you can do is like, you get to decide which cards you want to draw.
Exactly.
That's how Metropolis is.
Yeah. Yeah. Did anyone hear that? Everyone hear that answer? Okay, so I've got my cards. Someone offers me, multi-site Metropolis-Hastings says someone offers me another 5 cards, and I've got to decide whether to take the other 5 cards or stick with the cards I've got. A better way of doing things, maybe it's a different game, I don't know. Just show me one card and say, do you want to switch one of your cards for that card? And then I have to decide, well, which card should I switch? And so, right. For which card should I switch? That's a complicated thing to describe, to decide. Right? So what we do is just pick one at random. I'll switch that one. If I switch that one, does it make the hand better or worse? Then I figure out what the weight of this new hand is, and if it's better, I'll take the new hand with the card switched. Otherwise, I'll just stick to what I had before with some probability. So that's exactly multi-site Metropolis, single-site Metropolis-Hastings. We're going to pick one of our cards at random. We're offered a new card, and we decide whether or not to switch. Okay, the new card is called a proposal card. Okay, let's write that down, then let's write down the algorithm. And then we'll look at what happens. So we've got our old hand. Suppose we've got our old seeds or our old cards. We already have. Oh, it's given. Now what do? I draw From a categorical distribution, that means picking a number between 1 and n, and we could do it cleverly. We could figure out which one's a good one to swap and so on, but we won't. We'll just say with categorical uniform distribution across the numbers from 1 to n. Okay, 1 to n. Okay, so any number will get chosen with probability 1 over n, probability of any choice. So we get then, so we draw, let's say I. That tells us which card we're going to switch. And now we make the switch. Okay, so we pick a new, we draw a new card. And all our draws are now from the prior, according to our simplifying observation. So we draw SI from, all our cards are coming from the uniform distribution on the unit interval. And now we let the other things, SJ, be what they were before. So they're not, the other cards aren't changed, only the card we picked is changed for a new one. Okay, for J not equal to I. Okay, so now we have our new proposal seed. Now we can run the program. To run the program just means to find its weight and its result. So let's do that Metropolis step. So if, I feel like I had more lines in my notes, but no, that's cool. If the weight of this new hand, or this new seed, S prime, is bigger than the weight I had before, or I toss a biased coin whose bias is the weight of the new hand over the weight of the old hand. The old hand is the weight of the new hand over the weight of the old hand. And if that succeeds, then I need to push something out. What am I going to push out? I'm going to push out the results of using that seed. Output a spit. We say spit here. Spit. The result of S prime of the new seed. Otherwise, we spit the result with the previous one. Okay? So just as in the simple Metropolis-Hastings, we stick to the old value with some chance if it's not better than the new, if it's not worse than the new value. Okay. Let me number these lines a little bit more. Okay. So that's it. So I wrote this in Haskell. It takes about a similar number of lines, maybe slightly more with a little bit of bookkeeping, and we can see the output of it. So that's what you've been looking at all through, is this algorithm here and what happens.
Just briefly clarify, the result there, that's like applying the transformation that gets you the distribution you wanted from the uniform one?
It might be, but also remember in the example we talked about the bus where we weren't sure what the rate was. We had those extra parameters, variables in the prior. And we might marginalize some of those as well. So result is what, in the program we write, we have a return command at the end. So result is what the return command will return. Yeah. Yep.
When your program says spit result, does that mean it adds it to some list of samples?
Yeah, okay, yeah.
Okay, right.
Well, it's really a stream because it's going to keep going forever.
Yeah.
Yeah, you can look as far as you keep going.
Just keep doing that.
You keep doing that, yeah. I mean, as somebody said, it's a good idea to throw away the first 10,000 or so, or whatever. It's also a good idea to thin, because there'll be some correlation between the samples. Yeah. Okay, so should we have a look? So here I didn't do any burn-in, and I didn't thin, okay? Can you see this? Yeah, okay. So I think what it drew first was this point here, a bit of a rubbish point. Okay. Now in single-site Metropolis-Hastings, we only change one of the cards at once. In this case, it looks like it changed the B card, and it ended up here. And then I guess it changed it again and ended up here somewhere. And then maybe started changing, and then it was in a hotspot, right? So then it was reluctant to leave. So then maybe changed the A card a little bit, moved around. At some point it ended up out here, because with small probability we'll always jump somewhere that's rubbish, but then we'll probably end up jumping back again. And so we end up exploring. Okay, that was just in case you couldn't see that. Okay, so here's what it looks like when we zoom in. I think this is 1,000 samples, so it's an order of magnitude, 2 orders of magnitude less. Maybe it's 10,000. Okay, 1 order of magnitude less than what we had to do with the simulation to get the answer. And that's just with 2 dimensions. It gets even better as you scale up the dimensions. Okay. Can anyone notice anything not so good about this? Sorry? Anyone notice any problems with this? Yeah. Yeah, right. Yeah. So in this example, it's very, very well suited to this Metropolis-Hastings because there's only one mode, right? We want to end up in this area, and once we end up there, we're all good. Right? Maybe in another example, maybe the program regression example, the program induction example, there were loads of modes. Okay? So there'd be another mode over here, and if you end up over here, how are you going to get to another mode? So just imagine a mode over here, big area of dots. How are you going to end up over there? Well, you first have to go, let's call it hot and cold. Right? You first have to go through a really cold bit until you end up in the hot bit. Right? And that's something you're reluctant to do. So it will happen asymptotically, but it may take a very long time. Okay? So for a multimodal distribution, it may be that Metropolis-Hastings in this formulation doesn't find the thing very quickly. And also, you won't know up front how many modes there are going to be. So you won't know whether you to stop. So coming back to the question, yeah. Was there another question? Another point about what's bad about this as it stands? So this good region is quite parallel to the x-axis here. And that means when we're exploring it, we're quite likely to just move within the region, because we only change one axis at once, one dimension at once, one card at once. Yeah. What if the good area was on a diagonal? Then, in order to explore the good area, if the good area was a diagonal like this, we only change one direction at once. So in order to get from this point to this point, which is even better, we have to go outside the good area to a very cold area, and then go back. Well, that's supposed to be. We have to change the x thing and then the y thing, and that's unlikely that we'll do that. So it's not even multimodal. It's single modal, but we're still having to step into the cold bit before we get back to the hot bit. Sometimes you have to go down to go up again, but this is even within the same contiguous region. Okay. So there's things you can do about that, so-called adaptive Metropolis-Hastings. We'll figure out some transformation to do automatically to the state space, maybe rotating it or something so that you avoid this kind of problem. You can imagine that being some sort of program transformation or something that you do. Yeah. There's a few questions here. Yeah.
Can we just put a point on the sphere, like that sphere,
Yeah.
instead of drawing categorically uniformly?
Okay.
So, you have
Yeah.
and different dimensions you can go in and
Yeah.
sort of interpolate between them and pick a random one back.
Yeah. Oh, I see. Yeah, but that might be the sort of thing you might try with adaptive Metropolis-Hastings. I mean, this is going to be a 100-dimensional thing in the end, so I'm not sure that will work. But yeah, exactly. This kind of thing would be good to try. You're welcome to load up Haskell and try that. Yeah.
I'm not sure if I can voice this correctly, but how do we know that this algorithm gives us a better approximation of the posterior distribution as opposed to just amplifying things that are more likely?
Yeah. So amplifying things that are more likely is exactly what weighted simulation does.
Right.
Yeah. For a general program, we don't know anything. Yeah. We certainly don't know when it's reached an asymptotic distribution. We don't know when it's behaving better. So statisticians have, some of them will study particular models and find numbers that you need to look for to make sure things are converging. They also have methods, some of them are just visual methods of looking at things and checking that things seem to match up, and that tends to work, they think. But yeah, I think this is the Achilles heel, as I said, of general probabilistic programming as it stands at the moment. I mean, in practice, you saw the simple examples I showed. We didn't come into problems. And it's not, for example, the physics example, if I do this Metropolis-Hastings, it's, again, 10 times faster than weighted sampling. But, yeah. Yep. And?
Reinforcement learning.
Yeah, I'm not sure. I expect so. I'm not sure exactly what to say there. Yeah. Yep. Of the? Oh, yeah. So my program looks something like this. I compute the weight just like I do in weighted Monte Carlo. For every observation I see, as I run, I keep track of what my weight is, and I'm going to multiply it each time I see an observation. So every time I see an observation, I calculate the density function at the observation point. That's the normal distribution. Density function. Yep. And I multiply the weight as I'm remembering it so far by that likelihood. Sorry? It's a real number, real number between 0 and infinity. Yeah. Yep. The weight of the vector. No. The vector S. Sorry, right. All right, so it's a little bit more. Okay. So I've got a probabilistic program which has some random choices inside it, maybe 2 random choices. Given answers for those 2 random choices, the rest is deterministic. Okay, the rest of this, the weight and the result, is deterministic, given A and B. So if I fix A and B, I know I can tell you for sure what my weight's going to be. There's nothing random anymore. Okay. So now the seed, this S vector, the hand of cards I have, are those random choices that I'm going to do. So if I do all the random choices up front, I fix what they're going to be, I get a vector of numbers between 0 and 1, because I've used this idea that I'm just going to use uniform distributions. And so I've fixed that already, and then I run through, and everything's deterministic. So given the choices for A and B, I get back a weight. Yeah.
The inverse CDF only works for like continuous or smooth.
No. Works pretty general. Works. No. Right. So the inverse CDF method is part of a general idea in probability theory sometimes called noise outsourcing, sometimes called randomization, sometimes called a reparameterization trick in machine learning, and it works very, very generally. Yeah. I think who's first. Yeah.
So how is single-site image different from multi-site?
Yeah.
Because it seems that if the random number generator works well,
Yeah.
it seems to be of the same effect.
Right, so the difference is, let's see, right, so, sorry, are you asking how it's different in performance or just different in how it's written?
Like
what it does, I mean.
Theoretically.
Oh, theoretically, okay. So one intuition why it's better is if I seem to find, I don't know, if the idea with cards wasn't good enough for you. If I seem to be inside a hotspot, where are we? Yes, spot, okay. I seem to be inside a hotspot, then a good way to explore that hot area is maybe not, with multi-site MH, I just totally pick a totally different point, and then I either accept or reject that. With single-site MH, I move it in one direction only. So the idea is if I'm in a good region, I want to keep holding, this could be, here I only had 2 dimensions, maybe I've got 100 dimensions. If I just randomly pick a totally different point in 100 dimensions, I'm probably going to lose anything good I had. If I keep everything else the same, this is just intuition because everything asymptotically works well, but if I keep everything else the same except one point, I'm more likely to explore, intuitively, I'm more likely to explore a good region.
If it is a good random number generator, shouldn't be the case that if you change like a small bit in the seed, it will result in something.
I used the word seed, but I wasn't really talking about like kicking off a random number generator. Once this vector here is known, everything else is deterministic. Okay? So it's not that there's, unless you think of the CDF as some kind of number, but it's not really. Yeah, so I called it a seed, but really it's just everything else is really deterministic. Yeah.
I think I just rephrase it.
Yeah, okay, but it's a good idea.
So it seems like what you're more doing is finding high likelihood regions in the distribution as opposed to finding.
No, you are going to spit out the true posterior distribution asymptotically. Yeah. I want to say something about that, but I've. What else can Yeah, so it is an optimized, so I mean, this is answering a question, but it is an optimization algorithm. It's a noisy random optimization algorithm, Metropolis-Hastings. It's not finding like a line of best fit, it's finding a distribution, it's finding a posterior, and it's doing that by spitting out samples from the posterior. Yeah. Okay, so I think so what I was going to talk about briefly was what to do about getting rid of the simplifying assumption, but I think let's leave it at that. Let me just say a few words in conclusion. And we can talk. You're welcome to talk to me about. So the simplifying assumption was that there are only n sample statements. It's a pretty heavy simplifying assumption, okay? But there it is. Okay, we can get rid of that. It's not very hard at all, but I think we'll probably better go for a break. Let me just say, this is one inference algorithm, okay, and you can improve it. I guess you guys, coming from a different position from statisticians, maybe can think of new ideas of how to improve it that they haven't thought of, and get loads of credit and make lots of money or whatever. Okay, but there are loads of other simulation algorithms that are out there that are implemented for probabilistic programming languages. Monad Bayes has them. This is a paper where we talked about how to combine different inference algorithms. Anglican has them. Several other languages have multiple inference algorithms. So the idea is you write your model, and then maybe this very simple Metropolis-Hastings thing didn't work that well. You can then plug in a different inference algorithm and try it with that. So the model is kept separate from the inference. Okay. Are there any more questions before we go for a break? Yeah. Yeah, that's an interesting idea. Yeah. So somebody said rather than change one card, maybe change two cards. Maybe a good idea. Yeah. I don't know how much people have explored that idea. It's a good idea. Yeah.
It seems like what you're trying to do is build this model. You want to draw the linear regression. But at the end of the day, maybe you just care about finding the y or finding your x. The linear regression is just going to give you something. So why couldn't you do this in the original data space where you receive some data, and you want to output data that's similar to that with some variation?
Yeah.
Do you need to go through the machinery building a model, or can you just with some data generate some similar data like that?
Yeah. Well, there were certainly methods for doing that. Probabilistic programming is to have a clear model written down with the prior and the likelihood. Yeah, certainly I think it's increasingly the case that people are interested in seeing whether you can get rid of the prior as much as possible and just start drawing samples sort of similar to your data. Yeah, absolutely. Yeah.
You mentioned that Metropolis-Hastings talking about local mode, we
Yeah.
just don't know how many modes there are.
Yeah.
Will any of these more rapidly claim how many modes there are? If you didn't know how many modes there would be, what do you do?
Well, yeah, I mean, I don't know if I can really go into how these other algorithms work in the -9 minutes we have now. I mean, for example, Hamiltonian Monte Carlo works where we've seen this picture, where this sort of thing is smooth, which it is in this case. I could use Hamiltonian Monte Carlo on this example, and it's going to sort of, one way of thinking about it, you run a ball over the surface, which this is describing like a 3D surface, if you imagine it, and you kick that ball off with some momentum. And it's quite, I think Hamiltonian Monte Carlo will be quite good at finding modes just by, it will roll down out of the good area and then it will roll back into a good area. So, yeah. Or maybe I said down and up the wrong way around, but you get what I mean. Yeah. Okay, so this afternoon we're going to put this to one side and look at another thing which excites me about probabilistic programming, which is giving a meaning, a measure theoretic meaning to statistical models. Okay, so thanks.